Swayam Prabha. Digital India. Educated India.
Last two lectures, we dealt with similarity method for the velocity boundary layer. In lecture 6, we developed the similarity equation, and in lecture 7, we obtained solutions to the similarity equation. Today, we will deal with similarity method for the temperature boundary layer or the energy equation. And like before, we shall first establish the condition for existence of similarity solutions to the temperature boundary layer equation, and then derive the boundary conditions. So, as you will recall, the boundary layer form of the energy equation has convective terms on the left hand side, the diffusion term in the transverse direction, the viscous dissipation term, the pressure work term, and two heat generation terms, one due to chemical reactions, the other due to radiation. For our purposes presently, we shall ignore Q dot chem and Q dot rad. As we said earlier, U dP infinity by dx is important only in high speed compressible gas flows, and therefore, are presently neglected. So, the last three terms are neglected because we are largely dealing with uniform property in compressible flows. The boundary conditions to this equation would be at the wall y equal to 0, T will equal T wall, and that may or may not be a function of x. At y equal to infinity, T will be equal to T infinity and is assumed to be constant in the free stream. It does not vary with x. If we want to develop similarity equation, then first of all we define T w x minus T infinity, that is the reference between wall and infinity states, as some function g x, and we define theta eta, where eta is the similarity variable introduced in the velocity boundary layer equation, equal to T at any point in the boundary layer minus T infinity divided by T wall x minus T infinity, and eta, as you will recall, is equals y into under root u infinity by nu x. If I make the substitutions of these two quantities in the differential equation, I am going to replace T in these three terms by theta, then you will notice that dt dx will equal d by dx of T infinity plus theta into T w minus T infinity. Since T infinity is constant, does not contribute to derivative, and therefore, I would get T w minus T infinity d theta by dx plus theta into d by dx of T w, because T w is a function of x. dt dy likewise will be d by dy of T infinity plus theta into T w minus T infinity, and that would simply reduce to T w minus T infinity d theta by dy, and likewise d2t dy square will simply reduce to T w minus T infinity d2 theta by dy square. And therefore, upon substitution, you will see the equation would now become dividing through by rho Cp I will get u dt by dx plus v dt by dy equal to alpha d2t dy square plus mu by rho Cp du by dy square. If I substitute these three derivatives here, I will get Tw minus T infinity into u d theta by dx plus v d theta by dy plus theta into u dTw by dx equal to alpha into Tw minus T infinity into d2 theta by dy square and plus nu by Cp du by dy whole square. That is what I will get. If I divide through now, dTw by dx is nothing but dg by dx, and Tw minus T infinity is nothing but g. So, and therefore, if I divide through by g, I will get u d theta by dx plus v d theta by dy plus u theta by g dg by dx equal to alpha times d2 theta by dy square plus nu by Cp Tw minus T infinity du by dy whole square. So, this then is the last equation that you see here, and we now wish to represent each term in terms of similarity variables. For the velocity boundary layer, the similarity variables are u infinity equal to c x raised to m, eta as we saw before is y into square root of u infinity divided by nu x, psi is f eta into nx, a function of x. Nx itself is under root nu u infinity x, and we define u over u infinity equal to f dash. So, therefore, u will become equal to u infinity f dash, v which is equal to minus d psi by dx will become minus into f dash into nx into d eta by dx plus f into dn by dx follows from this definition of psi. D theta by dx would be simply theta dash into d eta by dx, where theta dash is d theta by d eta. D theta by dy would be equal to theta dash d eta by dy, and d eta by dy would be simply under root nu u infinity x. d2 theta by dy square would be d theta double prime u infinity nu x into du by dy whole square equal to that f double prime square nu x. So, you will see that if I now substitute for u d theta by dx and so on and so forth in this equation, u infinity into f dash into d theta by dx, which is d theta, which is theta dash d eta by dx minus f dash n d eta by dx plus f dn by dx into d theta by dy, which is theta dash into under root u infinity by nu x u infinity f dash theta divided by g dg by dx equal to alpha times u infinity by nu x into theta double prime plus nu by Cp T wall minus T infinity into u infinity cube by nu x into f double prime whole square. Now, notice that dn by dx, since n is equal to under root nu u infinity x and u infinity is equal to c x raised to m and eta is equal to under root u infinity by nu x. So, I can show that n is equal to n divided by nu x, which will be under root u infinity nu x. So, remember, if I were to replace this n by n nu x u infinity by nu x, then you will see that I get u infinity f dash into theta dash d eta by dx minus f dash n is equal to under root nu u infinity x d eta by dx plus f dn by dx into theta prime under root u infinity by nu x. And therefore, you will see this becomes u infinity f dash into theta dash d eta by dx minus f dash into theta dash u infinity d eta by dx plus f theta prime under root u infinity by nu x dn by dx. And therefore, you will see this term gets cancelled with this term, and I essentially have now minus f theta dash, this is the left hand side, the f theta dash into under root u infinity by nu x dn by dx plus f dash u infinity theta by g dg by dx equal to alpha u infinity by nu x theta double prime plus nu by cp t w minus t infinity u infinity cube by nu x into f double prime whole square. This would be the equation. You will see these two terms now get cancelled. U infinity by nu x, as you can see, is simply n over nu x. I divide through by u infinity by x, then you will see you will get minus f theta prime into under root nu x by u infinity dn by dx plus f dash, but it is quite correct, n and n will get cancelled and this term gets cancelled with that one, and minus theta dash n f dn by dx is equal to all this. Yes. So, my purpose is to then yes, correct, f dash theta, and this will become u infinity squared because I have divided through by this. So, this will go and this will go, and I will get u infinity by nu x is really n over nu x, and that is how this and this term gets cancelled. So, essentially you then have this term f dash theta d divided by g x, and multiplying through by x, I get f dash theta x dg by dx minus f theta dash x over n dn by dx equal to, that is this term, theta double prime divided by Prandtl plus 2 E c x f double prime square, where Eckert number E c x is defined as u infinity square divided by 2 divided by Cp into Tw minus T infinity. Now, to show this x over n dn by dx equal to m plus 1 by 2, well, that is a straightforward thing. N is equal to under root nu u infinity into x, but u infinity is equal to C x raised to m, and therefore, this becomes nothing but C times nu x raised to m plus 1, and that is equal to under root C nu x raised to m plus 1 by 2. That is n. dn by dx therefore, will be under root C nu into m plus 1 by 2 into x raised to m minus 1 by 2. And therefore, x divided by n dn by dx will be equal to x divided by under root C nu x raised to m plus 1 by 2 into under root C nu into m plus 1 by 2 into x raised to m minus 1 by 2. So, you get this and cancelled with that. This is x raised to 1. So, this becomes x raised to minus 1 by 2. So, this and this gets cancelled, and you simply get m plus 1 by 2. That is what is shown here. This is the pressure gradient parameter m, and therefore, our equation would become like this. I have transferred the terms, all terms on the right hand side and multiplied through by Prandtl number. Then you will see our equation becomes theta double prime plus Prandtl into m plus 1 by 2 f theta dash minus f dash theta x d by g dg by dx, which is the wall temperature variation function, plus 2 E C x f double prime square equal to 0. Now, as we said before, this equation will be a perfectly ordinary differential equation if this quantity x divided by g dg by dx is a constant. Let us say it is gamma. Then the solution to g will be simply Tw minus T infinity is equal to some delta T ref, yes, x by g dg by dx equal to gamma gives me dg by g is equal to gamma times dx by x, and the solution therefore is g times some constant delta T ref into x raised to gamma. So, unless the wall temperature variation is of this form, gamma is an arbitrary constant, of course, then similarity solutions will be possible. Likewise, E C x should also be a constant, but what is E C x? E C x is u infinity squared by 2 divided by C p into Tw minus T infinity, and this is equal to C squared x raised to 2m divided by 2 times C p, and this is delta T ref x raised to gamma. G is Tw minus Tf, which is G. G is that, and therefore, E C x will be constant. If this is constant, then this and this must cancel, which means gamma must equal 2m if E C x is not equal to 0. So, remember, similarity solutions to the temperature boundary layer are possible when E C is ignored, that is viscous dissipation is ignored, then gamma can take absolutely arbitrary values. Viscous dissipation is included, gamma can take only restrictive values, gamma equal to 2m. This is because there is a connection between the viscous dissipation term and the velocity solution. Such odd constraints are put in similarity method. So, these are then the conditions for existence of similarity solution is that the wall temperature variation must follow this law, must be proportional to x raised to gamma, and ECX, if ECX is included, then gamma must equal 2m. So, then our final energy equation is of this time: theta double prime plus Prandtl m plus 1 by 2 f theta dash minus gamma f dash theta. This is represents the wall temperature variation, this is the viscous dissipation, and this is the pressure gradient, and this is the Prandtl number, with a reminder that where EC is equal to this, and if EC is not equal to 0, then gamma is equal to 2m, otherwise gamma can take absolutely arbitrary values. What would be the boundary conditions? Well, that is straightforward to see if you recall the temperature. So, at the wall eta equal to 0, theta 0 will be 1, and at infinity state the numerator will be 0. So, theta infinity will be 0. So, that is what you see here. So, the boundary conditions are this, and what would the solutions look like? The theta eta will be functions first of all m and bf, because f, f dash and f double prime are functions of m and bf, and in addition you have Prandtl number, the wall temperature variation parameter, and the viscous dissipation parameter EC. This is what we expect. How do we solve this second order differential equation? Well, like we did in the case of velocity boundary layer, where we had a third order equation. So, we split this up into two first order differential equations. The first equation is simply d theta by theta equal to theta dash, with theta 0 equal to 1, which is known, wall temperature is known, and then d theta dash by theta equal to theta prime, which is equal to minus Prandtl all this, but without knowing theta dash 0, we do not know the theta dash 0. So, like we did in the velocity boundary layer equations. So, first of all we obtain for a given m and bf gives f, f dash, f double prime. We then guess theta prime 0 and solve these two equations by Runge-Kutta method from eta equal to 0 to eta equal to eta max. At each iteration, we check the boundary condition at the outer edge, whether theta eta max has tended to 0 or not. If not, we revise theta dash 0 and continue the solutions again. When the solution is obtained, we define thicknesses of the temperature boundary layer. The physical thickness delta is, remember our solution will look like this: theta versus eta. At wall it will be 1, and we expect the solution to go something like this, with a 0 boundary condition at eta equal to some eta max. So, how do we choose the value of the thermal boundary layer thickness? So, just as we choose velocity boundary layer thickness and say that when f dash eta tends to about 0.99, we say that is velocity boundary layer thickness. Likewise, in temperature boundary layer, we say when theta tends to about 0.01, that is somewhere here, then theta, then that would represent, but there is a notional thickness, there is no exactness. We can impart exactness by defining another thickness called the enthalpy thickness, and it is simply represents 0 to infinity rho Cpu T minus T infinity, which is the actual enthalpy within the boundary layer when integrated dy, and this is the enthalpy that would be carried in the layer if there was no boundary layer. For uniform property flow, where rho Cp gets cancelled with this, u over u infinity will be simply f dash, and T minus T infinity over T wall minus T is our theta, and therefore, this relationship, if I change y to eta, then delta 2 star delta 2 by x into Reynolds x to the minus 0.5 equal to 0 to eta max f dash theta d eta. This is the dimensionless form for a uniform property enthalpy thickness. Remember, we obtain solutions by guessing the value of theta prime 0. How is it related to the heat transfer coefficient? Hx, the local heat transfer coefficient, will be q wall divided by T wall minus T infinity. Remember, at any x, if this is Q wall, T w and T infinity, then H x is simply Q w divided by T wall minus T infinity. This is the definition, you will recall, and that would equal, if this was the temperature profile, the gradient of temperature. Therefore, this will be minus k dt by dy at y equal to 0 divided by T w minus T infinity. But notice, I can, since theta is equal to T minus T infinity over T w minus T infinity, I can straight away say this is equal to minus k d theta by dy at y equal to 0. This is dt divided by T w minus T infinity. And if I now change eta is equal to y times u infinity by nu x, then you will see this can also be written as minus k d theta by dy d eta into d eta by dy at y equal to 0, and that is equal to minus k theta dash 0 into under root u infinity by nu x, under root nu infinity by nu x, which I can develop further as h x into x by k, which is how I define the Nusselt number nu x. Then you will see this becomes equal to minus x by k into k theta prime 0 into u infinity by nu x, and you will see k and k gets cancelled, and you will get this as minus theta prime 0 into under root u infinity x by nu, and that is nothing but minus theta prime 0 Rex to the half. And therefore, I can say that nu x Rex to the half minus half is equal to minus theta prime 0. Our RK solution essentially gives us the value of theta prime 0, which in turn gives us really the value of Nusselt number. That is what I have derived here, nu x is equal to that. Sometimes in boundary layer theory, we define Stanton x, St, and say nu is Nusselt, named after the scientist Nusselt. Similarly, St is Stanton, named after a scientist Stanton, and that is defined as h x divided by rho c p u infinity. Remember, there is no length dimension in the definition of Stanton number, and this is found sometimes quite useful in defining a dimensionless heat transfer coefficient. It is simply Nusselt x divided by Reynolds x into Prandtl. It is a simple algebra to show that if I divide this quantity by Reynolds x and Prandtl, you would get Stanton. So, then the solution is essentially Nusselt x or Stanton x is a function of m b f Prandtl gamma E c, and with a reminder, if E c is not equal to 0, gamma is equal to 2m. Knowing local value of h x, you can always calculate average value of heat transfer coefficient and average value of Nusselt number. So, here is the first solution obtained to the thermal boundary layer equation. Taking the case of a flat plate means m equal to 0. No suction blowing means this means Bf is equal to 0. Constant wall temperature, this means gamma is equal to 0. No viscous dissipation, this means E c is equal to 0. So, we have a very simple equation then, theta double prime plus Prandtl into f theta dash divided by 2 equal to 0, and the velocity equation would look like f triple prime plus half f double prime equal to 0. So, if I now in addition say besides these that Prandtl number is equal to 1, then theta double prime will equal 1 by 2 f theta prime equal to 0. The boundary conditions here are f 0 equal to f dash 0 equal to 0 and f dash infinity equal to 1, whereas the boundary conditions here are theta 0 equal to 1 and theta infinity equal to 0. You will see therefore, that there is a remarkable similarity between these two equations, and if I were to say that theta eta equals 1 minus f times eta, then I do not have to solve the temperature equation, simply the value of velocity boundary layer equation itself will show me that. So, you will see here earlier solution for f dash, this is the velocity boundary layer equation for Prandtl equal to 1, and boundary layer thickness for the velocity was about 5. Likewise, the temperature profile theta is going, this should be 1 minus f dash eta. So, theta is nothing but 1 minus f dash eta, and this is the f double prime 0, which is going so, and here is theta prime at x equal to 0. So, this shows that perfect analogy between heat and momentum transfer exists for Prandtl equal to 1. Remember, Prandtl is just simply nu by alpha. So, if this is equal to 1, the rate of diffusion of momentum and heat are equal, and we say in such a case there is a perfect analogy between heat and momentum transfer, and all thicknesses would be equal. So, thermal boundary layer thickness delta star would equal velocity boundary layer thickness delta star, enthalpy thickness delta 2 star would equal momentum thickness delta 2 star, minus theta prime 0 would simply equal f double prime 0 as seen in the figure here with a negative sign. You see, this is theta prime 0, theta dash 0, and this is f double prime 0. That is what you see here. This reference case is of great value to us, because we can now go on comparing the effects of M, BF, gamma and EC and Prandtl number on solutions. So, here are the solutions generated by Rangakatta computer program, and what I have now done is allowed for the variation of Prandtl number by keeping M, BF, gamma, EC all equal to 0. So, we have case of flow over a flat plate at constant wall temperature, no suction and blowing, and viscous dissipation is ignored. Then you see value of minus theta prime 0 for I have computed from 0.7 to 25 as the Prandtl number. So, you see at Prandtl number 1, this is the well known velocity solution really, where perfect analogy between momentum and heat transfer exists, 0.33, 4.92 and but when the Prandtl number is reduced to 0.7, which is for the gas, you get theta prime 0 is lowered to 0.291, the thermal boundary thickness increases, and so does the enthalpy thickness increase. On the other hand, at 5, which is more or less water, you get higher heat transfer rate, 0.572, 2.73 and 231, still higher 0.721, 2. And these are really the organic liquid range in which this still increases. So, you have minus theta prime 0 increases with the Prandtl number. So, minus theta prime 0 is NUX REX to the half. Now, if I were to correlate these values theta prime 0 as a function of Prandtl number, I would see that it will become 0.33 into Prandtl raised to 1/3, and therefore, you can develop from the numerical solutions or the similarity solution an expression for Nusselt number as NUX is equal to 0.332 Reynolds x to the half Prandtl to the third. This result looks remarkably like an experimental correlation. Indeed, this result has been found to be in excellent agreement with the experimental data. One point to note, however, is that delta star, the thermal boundary layer thickness, increases with decrease in Prandtl number, or another way of saying, thermal boundary layer thickness decreases with increase in Prandtl number. And therefore, as we move towards oils and other things, where the Prandtl number is very, very large, you would see that the thermal boundary layer thickness would be much, much smaller than the velocity boundary layer thickness. So, in other words, as we move towards oils, which is Prandtl number very much greater than 1, then you will get situation like so. This will be the velocity boundary layer, and the temperature boundary layer would just develop like that. On the other hand, for liquid metals, when Prandtl number is very much less than 1, then you will get this with the temperature boundary layer, and the velocity boundary layer will be this. So, here delta is much, much smaller than delta, whereas here delta would be much, much greater than delta. This important deduction we will make use of it in several further developments of both the similarity method as well as the integral method that we will be discussing much later. So, with this I have given you a simple sample solution for a very special case of m equal to 0, Bf equal to 0, gamma equal to 0, Ec equal to 0. In the next lecture, I will explore the influences precisely of these parameters on heat transfer rate.